Hi class, this is Joseph. We are in chapter 6 of Hurley's Introduction to Logic, 6.2. So today we'll be talking about truth functions, and let me get to it. And what I was going to say too is, last lecture I didn't say this, but if you're in my logic class, some of you do better in certain areas of logic than you do others. For example, chapter 2 dealt a lot with linguistics, language, meaning, chapter 1 dealt with argument forms, inductive versus deductive. Chapter 3 dealt a lot with fallacies where there was a defect in the content. And chapter 6 is very mathematic in nature, you might say. So if you're good at mathematics and geometry, you might do very well in this chapter, whereas if you weren't as good with the other chapters. So I'm just saying some of you have different skill sets. So this is like solving puzzles when you figure out in this section what each of the 5 logical operators do. We'll assign them truth values and then figure out, okay, this is either true or false now. And then when we get to the next part of the chapter, we'll find out what role they play inside arguments as a whole. But for now, we'll start off with the truth functions themselves. And like I said, this is a review of chapter 6.1 when we talked about the 5 logical operators. One was a tilde, the other one was a conjunction, a disjunction, a conditional, and then a triple bar. And each one of those had a certain function. So today, let me just read to you. Start here. And I'll do something a little differently this time. I'll do this video explaining the theory behind the chapter, and then I'll make another quicker video on like how to do homework examples. So we'll break it up into 2, okay? All right, so I'll read you. How logical are you? Oh, sorry, I love doing this. I have to put this little bad boy on. There you go. How logical are you? Suppose your instructor made this promise. If you get an A on the final exam, then you will get an A for the course. Now, right there, when you see that if-then, what kind of logical operator do you think is functioning there? A horseshoe, yeah. This is the conditional statement. There are 2 possible truth values for the antecedent. It's either true or false. And there's 2 possible truth values for the consequent. It's either true or false. So there's 4 possible combinations in all with just 1 conditional. And by the way, if I say conditional or I say horseshoe, I'm simply referring to the same thing. The horseshoe is the actual symbol and the conditional is the name of it. Under what combination of truth values would you say your instructor had lied? We'll find out later on in the chapter. It gets a little deeper, and I'll read you a paragraph. But for now, just think of this little mini lecture as me telling you about the truth values of each of the 5 operators. All right, so a truth function is any compound proposition whose truth value is completely determined by the truth values of its components. This first part of the section, and by the way, I'm not reading everything with Hurley. I've already assumed you've done the reading. And then by the time you listen to my mini lecture, I kind of unpack it. Or you listen to this first and then you read more. Because as always, Hurley will give you more examples than I will. And that's why I love the text. But anyways, first part of this section presents the definitions of the 5 logical operators. The second part shows how they are used to compute the truth values of more complicated propositions. And the third examines further the degree to which symbolized expressions match the meaning of expressions in ordinary language. All right, here we go. Definitions of logical operators. Statement form. You can read this. I will just... What Hurley does is he'll use these lowercase letters, P, Q, R, S. They really are the same as using uppercase letters for propositions. And I'll show you this when I give you the example of how to do your homework video. But for now, let's say he's really redundant. He'll use this to give you the truth values, but then you're just going to apply them to a statement. So you could skip using the lowercase and just go straight here and apply your truth values. But I'll show you an example. Okay, now let's consider the definition of a tilde operator. Remember that one? It was a negation. So if you have something and you say it's not the case that, you're negating it. This definition is given by a truth table. an arrangement of truth values that show in every possible case how the truth value of a compound proposition is determined by the truth values of its simple components. All right, a lot of words there. So he says, let's just take any statement about reality. It's either true or false. Then we're going to negate it. And then you take the opposite. So let's say, well, I'll show you an example below. It'll be more clear. But he's saying, whatever this is, we're going to negate it. It'll be the opposite. Straightforward, 5th grade, addition. Very easy to comprehend. But now let me give you an example. So, I'll read the highlight. The truth table shows that not P is false when P is true. And not P is true when P is false. Now, what do we mean by that? Let me give you 2 examples. Let's read this. Again, this is a statement about reality, right? It's either true or false. It's not the case that McDonald's makes hamburgers. I'm saying it's not the case that McDonald's makes hamburgers. Now, you could translate this whole thing as an M, which Hurley does, and then you negate it, right? Because it's not the case, so you simply put not M. Now, when you do that, because remember, chapter 6.1 was all about, or section 6.1 was all about giving us this. Like, how do we get it? So this is just review, right? Now we're going to look at this and say, is it actually true? And in order to do that, we got to figure out what operator is it using. Well, it's using tilde. And as we see later on, we'll see conjunction, we'll see disjunction, conditionals with a horseshoe, and then we'll see triple bar. In each case, we're going to be looking at examples that we have seen in 6.1, like these guys. But now we're going to look at this and say, okay, is that true or false? Okay, so it's just an added layer. All right, so here we go, tilde. Is it the case that McDonald's makes hamburgers? Yes, and this is saying it's not the case. So we know that this whole thing is false, because that is a symbolic representation of a statement that talks about reality. And in that statement, it says something like, hey, McDonald's doesn't make hamburgers. Well, we know that's all false. They do make them. So you would just say it's not M is false. You would say M by itself. That's true. M, if we took out this not right here and just said it is the case that McDonald's makes hamburgers and we symbolize that as an M, we'd say that's true. Let's do this one. It's not the case that Starbucks makes hamburgers. We could symbolize this whole thing as an S, right? Again, review 6.1. I told you to take the first letter of the main word you see. You could use an I, right? Or you could use an S for Starbucks. So S, and then not the case, so not S. Now, we know Starbucks makes coffees, but it's not just that. They make a whole bunch of stuff. But as I checked last time, they actually don't make hamburgers. So it turns out that this is true. Even though it says not S, yeah, that whole thing's true. It's not the case that Starbucks makes hamburgers. Yep. If they did make hamburgers, that whole thing would be false. Okay, so this is just an example now of 6.1 and 6.2 in effect. 6.1 is you translate, you symbolize. 6.2, which one we're in now, you give me the truth value. Okay, and again, I'll show you homework examples, more of them in this second video. But here we go, conjunction. Here are the rules for conjunction. Now, let's say you have a P and a Q, or, down in these examples, you have capital letters. Like I said, Hurley's redundant. This is the same as this. Pick any 2 letters you want. It's the same as him picking a P and a Q. He's just saying very generally, when we have a conjunction, we have 2 conjuncts, or 2 sides of this. So P or Q, we have 2 of these guys. They're called conjuncts, right? And each one of these conjuncts is going to have a truth value. Depending on each one of these conjuncts, then the logical operator, this conjunct right here, then you're going to solve for it. Now, if you look through, the only time that the entire conjunction is true is when both conjuncts are true. Both have to be true, no matter what. And then you can get this whole conjunction to be true. If any one of these is false on any side, the whole thing's false. Okay? So basically in this section, you just have to memorize the rules, all right? If you debate these rules, you're debating over 2,000 years of logic and logicians coming up with the rules. Don't do it. You can do that later when you get into a graduate level program and you take symbolic logic. Even then, you won't be debating this. Okay, so There's the rules for negation. You have something, you negate it. You take the opposite value. So if I have a false, I'm negating it, it's a true. If I have a true, I'm negating it, it's a false. All right. Conjunction. The entire conjunction is true only when both conjuncts are true. If any one of them are false, so we have a true and a false here, the whole thing's false. We have a false and a true here, the whole thing's false. We have a false and a false, the whole thing's false. Okay? So let's come down. Now let me give you some normal English, right? Ferrari and Maserati make sports cars. Let's translate this. He does it for us. F.M, right? How do we get the dot? Because we have an and that was one of our rules. We have and. We have a bunch of words we can use, but in this case, it's an and. You can go back to the end of 6.1 and see that little summary of all the possible words and what symbols they get. So is this the case? Do Ferrari and Maserati make sports cars? So it's true and it's true. So the whole thing is true, right? Because both conjuncts are true. What about Ferrari and GMC make sports cars? So Ferrari will do F and then GMC will do G. Okay, F.G. So is it the case that Ferrari makes sports cars? Yes. So we have a conjunct that's true. And then what about the second one, GMC? Do they make sports cars? As we know, and if you didn't know this, you just have to look it up. They don't. So this is false. So we have a true and a false. So what's the whole truth value of this conjunction? False. For the second one, right? Because if we have any side that's false, the whole thing's false. They both have to be true for the whole thing to be true. Okay? So let's do this last one. GMC and Jeep make sports cars. This is just a shoot down right away. This is false and false. So we have G and J. Both are false. So the whole thing is false. Pretty easy, right? Just memorize the rule. And there's different ways of memorizing. You might want to memorize, which ones are the falses, and that way if you know it's not false, it's true. For me, on the conjunction, I just memorize, what does it make for this whole thing to be true? Both have to be true. And then I just say, if any one of these sides are false, the whole thing's false. So, for example, if I see that this side, let's go down here. If I know I'm dealing with a conjunction, and I know that both conjuncts have to be true, if I know that GMC do not make sports cars, I know this one's false, do I have to go to the other side and solve it? I'll let you think about that for a second. If I know one of them's false, do I even have to look at the other one when I'm dealing with a conjunction or a dot? The answer is no. The second you find a false, done. The whole thing's false. Why? Because we know if we have one false in there, the whole thing's false. Okay? All right, let's go to disjunction. These are our big ones, either ors, or just the word or is good, right? And then you get a little disjunction symbol, or the symbol itself is called the wedge. Okay, there you go. For this rule, at least one side has to be true for the whole thing to be true. At least one side. And the only time this thing is false is when both sides or both disjuncts. Remember how these guys were both called conjuncts? These are called disjuncts, and this whole thing is a disjunction. So the only time this whole thing is false is when both sides are false. So if you get one side true, the whole thing's true. You can look at this. So I got a true and a true, the whole thing's true. One side's true, the other one's false, no problem. Whole thing's true. That's why we use the word either or, giving you two possibilities, either or. It's either one or two. Is one of these true? One of those are. You're good. So let's give you some examples here. Either Stephen King or Kate Blanchett is a novelist. We know, so we can symbolize this as S wedge C. Pretty easy, right? We know Stephen King's a novelist, right? We know that's true, so therefore the whole thing is true. Is Kate Blanchett a novelist? I actually don't know. I'd have to look that up. But it doesn't even matter if that's true or not. It just doesn't matter because we already know this side's true. And according to this, as long as we have one side true, the whole thing is true. Let's do this one. Either Stephen King or Daniel Steele's a novelist. Well, again, we already know the first side's true. We don't even have to look at this side. And by the way, in both of these are this person could be a novelist and Danielle Steele could be a novelist. It's still true. Because again, you could have both sides true, and it's still true. Or you could have one side true, and it's still true. So again, you just look at one of these, you find if it's true, the whole thing's true. What about this one? Either Kobe Bryant or Tiger Woods was a novelist. Was Kobe Bryant a novelist? Like, he was world famous in basketball, and last time I checked, he wasn't a novelist. What about Tiger Woods? World famous golfer, not a novelist. Both sides are false. Kobe for, K for Kobe, T for Tiger Woods. Both sides are false. So the whole thing is, yes, I'm proud of you. Whole thing's false. Okay? So that's the rule on disjunction. You can read about this exclusive disjunction, and it talks about ordinary language. I'll let you read about that, which is important. And what I'll do is I will even highlight it. And once again, I won't exhaust everything in these sections, but I'll point out what I think is important. So I'd read about that up here, and then these examples. What I wanted to say, right here. Inclusive, all-encompassing, or exclusive. These two are going to be talked about by Hurley. And what's the difference? Okay, so conditionals. All right. So we have if-thens. We know they're like this. They're a horseshoe symbol. They imply something. This side is sufficient. This side is necessary. Remember that whole SUN acronym that we were using in 6.1? Well, okay. So how do we get the whole thing to be true or false? Look at the pattern here. This whole conditional is only false under one circumstance, only one, and that's when you have the antecedent, or this P is true, and the consequent is false. That is the only time it's false. Any other time, it's true. So what I would have you do is memorize when it's false, and it's very simple. Left side's true, right side's false, whole thing's false. If the left side's false, the whole thing's automatically true. Now, some of you might be saying, how could I have a false antecedent and a true conclusion? We will cover that in a minute. So, again, if I have a true antecedent, true consequent, whole thing's true. If I have a true antecedent and a false consequent, whole thing's false. That shuts down the operation of this whole operator of the conditional. If I have the antecedent false and then the consequent true, whole thing's true. If I have, and this, some of you are thinking, what is going on to me right now? What is happening to me right now when Joseph says, I have an antecedent that's false and a consequent that's false? How in the world could the whole thing be true? Again, we'll explain that in a minute. Okay. So that's it. Number one rule, you got to find out when it's false. And some of you have different ways of memorizing this. Here's the bottom line. You just have to memorize it. Or when you're looking at your homework in MindTap or in the book, you do your own little cheat sheet and you come back. And this brings me to, oh, never mind. I won't go there. At the very end of the chapter, I think there actually is a cheat sheet for all these conditionals. You can look at it or just write it down. And by the way, from here on out for the rest of the chapter, you're going to know these very, very well. They'll be burned in your brain because you'll be looking at them over and over and over. So this is why I give you the friendly warning is you must learn these now, because if you don't, when you get into 6.3, 6.4, 6.5, if you don't know the rules on or the truth values of these operators, you will definitely have compounded confusion. So you might think that 6.3, 6.4, and 6.5, they build onto this section. So you got to know this, okay? All right. So let's look. If Nicole Kidman is an actor, then so is Meryl Streep. So we have an if, we have a then. So we know the if is the antecedent. So we just put an N, then our horseshoe symbol, then the M. Okay, no problem. So, and then this one, if Nicole Kidman is an actor, then so is Wolf Blitzer. So we have an N and W. And then so he's just going to symbolize these. And now we're going to look at them. So is Nicole Kidman an actor? Yes, it's true, right? Then so is Meryl Streep. Is Meryl Streep an actor? I actually forget, so let me look. And by the way, if you didn't know, you just have to look it up. It's fine. Let's do this. Actress, boom, immediately pulled it up. Okay, so let's go. So we know this is a true and a true. So a true and a true. We look up here, true and a true. The whole thing is true. So this symbolic representation of this statement, which is true and false, it itself is true. Okay? And again, why are we doing this? Well, we're going to see later on in the chapter there, we're going to look at an argument in its most simplest form and in a mathematical sort of way, figure out the truth value of the whole argument, whether it's valid or invalid, and whether it's sound, just by being able to break it down into its simplest form. Let's look at this one. If Nicole Kidman is an actor, then so is Wolf Blitzer. We know Nicole Kidman's an actor, so this is true, the antecedent. What about Wolf Blitzer? He's some news dude on CNN, I believe, or he was. So we know this is false. So true, false, and it happened that was the only time the whole thing was false. So we know this conditional, this if-then statement, is false. Okay. And then let's do this. If Wolf Blitzer is an actor, then so is Jennifer Aniston. Well, we know this is true on the consequent, and we know Wolf Blitzer is not an actor, so we have a false, then a true. And it turns out that this whole thing is true because even though Wolf Blitzer is not an actor, and even though Jennifer Aniston is, it turns out that him not being an actor doesn't negate the fact that she is, or that would be a consequent. So for that part, let me show you this section. So this guy right here, you'll see why you could have a false antecedent and still have the whole conditional be true. Because what he's going to do is give you all four possibilities. And what are they? These. He's going to give you all four possibilities of truth values, right? He's going to go one by one and say, hey, I'm going to give you an example of your professor talking to you about your final exam and your final grade in the class. And I'm going to give you only one case in which he actually lies to you. So this if-then statement doesn't come true. But in all the other cases, it turns out they could still happen. He's not lying to you. So you could see these examples in light of this one. If you still don't get it, don't worry. You don't need to understand the linguistics behind this necessarily. You just need to memorize the mathematical operations of the truth value. So for purposes of this chapter, you just have to memorize this. When's this whole thing false? When's the whole thing true? But if you're like me and you're inquisitive and you want to go the one step further and say, but why? But why, Joseph? Come down here, okay? So let me read it to you. For an intuitive approach to this problem, imagine that your logic instructor made the following statement. If you get an A on the final exam, then you will get an A for the course. You could think of that as conditional, right? It is. How would you represent that? You could represent that A, horseshoe, C. And by the way, this is a good example of me telling you. So when you look at this side, you think you want to represent it as an A. Don't represent the other side as an A because it's different. You will get an A for the course is different from an A from the final exam. So this is the case that I would tell you, and so would Hurley, you use a different letter. So if you're going to use an A here, use a different letter here. So I say C. So basically, A, horseshoe, C. So A, horseshoe, C, right? And instead of talking about actors and all that, we're going to be talking about, or up here you might say, A, horseshoe, C. We'll talk about all the possible truth values on how I'd be lying to you versus not lying to you. Okay. If you get an A on the final exam, then you will get an A for the course. Under what conditions would you say your instructor has lied to you? Clearly, if you got an A on the final exam, meaning if that antecedent was true and you did not get an A for the course, you'd be like, dude, this guy lied to me, man. And that's just looking at the English and saying, hey, I got an A on the final exam. You said if I got this, you said that I'd get an A in the course, but I didn't, dude. So therefore, you're lying. So let's go back. Let's go further. So let me repeat. Clearly, if you got an A for the final exam, but you did not get an A for the course, you would say that she had lied, or me. This outcome corresponds to a true antecedent and a false consequent. On the other hand, if you got an A on the final exam and also got an A in the course, you would say that she had told the truth. There's a true antecedent and a true conclusion. But what if you failed to get an A on the final exam? Like, what if the first part of this antecedent, what if it was just false? Like, so now we're at this stage. Well, it turns out you could still get an A in the class. Let's say you were like wicked smart. Everything you did in law, you just aced it, right? But you bailed the final exam. So this part was false, but you still got an A in the class. Well, the whole thing's still true, because you wouldn't say I lied to you. So let me read. If you got an A in the course anyways, false antecedent, true conclusion, or you didn't not get an A for the course, false antecedent, false consequent. So if you bomb the final exam and you bomb the course, I didn't lie to you, because you didn't satisfy the first condition that I said you had to get an A for the course. You had to get an A for your final exam in order to do that. So in neither case, though, would you say that your instructor has lied to you. Given her the benefit of the doubt, you would say that she had told the truth. And if I could find an example of this on YouTube, like another video, you listen to it over and over, I'll post that as well. But for now, just go back and read this over and over. It'll make sense. But again, you don't need to know exactly why this is the case in order to get through this section. But again, we're dealing with logic and we want to have consistency with our beliefs. So if you want to ask that further question, why, here it is. All right. I've explained that ad nauseum. Thank you. All right. Biconditional, the last one. This is pretty easy. So on this one, in order for the whole thing to be false, one side has to be false. In order for the whole thing to be true, both sides have to be either true or both sides have to be false. So memorize this how you want. I would just memorize it like both sides have to be the same. Both sides have to be false or both sides have to be true. The whole thing's true. If one of these is opposite of another, the whole thing's false. Okay? So just in purposes of memorizing the biconditional truth values, that's it. And I'll read you what Hurley says. The truth table shows that the biconditional is true when its two components have the same truth value, and otherwise it's false. Real easy, right? So Bill Maher is a show host if and only if Jimmy Fallon is. So again, the if and only if, they represent the triple bar. And this is a biconditional. What it is it's two conditionals going the opposite way. So if you could see this in your head, this would say B horseshoe J, and it would say J horseshoe B. And when you have both conditionals going the opposite way, you have a biconditional. If that was too much for some of you, no problem. You can look here. P horseshoe Q and Q horseshoe P. I have both of those going on at the same time, then I simply have this. And he explains all that right here. So, but now let's say you have a symbolic representation of reality. This is the statement that talks about reality. You know, is the whole thing true? I don't know. Let's look. Bill Maher, he's a show host. Is he? I think so. And then is Jimmy Fallon a show host? Yep. So both of these are true. So the whole thing's true. Let's do this one. Bill Maher is a show host if and only if Emma Watson. I think she's an actor. So E would be false. This would be true. They're opposite of each other. So the whole thing's false. Okay? So I would say I've done all five ways that you can see how your operators are true or false. You got your rules up here. Negation is simply whatever you have, you take the opposite. Conjunction, both sides have to be true. If one of these conjuncts is false, the whole thing's false. Disjunction, at least one side has to be true, and then the whole thing's true. Conditional, the only time it's false is when you have a true antecedent is false conclusion. Anytime else, boom, whole thing is true. Biconditional, both sides have to match. False, false, true, true, whole thing's true. If you have one side that doesn't match with the other, whole thing's false. Oh, yeah. So computing the truth value of longer propositions, all that's saying is, hey, up above, I gave you examples when you just had one operator, right? Now Hurley's going to give you 2. He's going to say, you have to compute the truth value of this guy and this guy. Well, which one do you do first? Everything in the parentheses. Do everything in the parentheses first, then you get your answer, then you do the horseshoe symbol. So he's going to break this down very slowly all the way to the end. And I'll do one of these with you, and then we'll do examples in your homework. Okay, so A or D, it turns out you don't actually have to know anything about the linguistics of these. It turns out that he could just say, look, he could say, take this example, your A, D, and E, and he's going to give you the rules. A, B, and C are true. D, E, and F, they're just false. So substitute. He just said A, B, C are true, right? So my A is a true. My D is a what? A false. And my E is a false. So now I have a true, false, false, right? I have my truth values, right? Now I have my symbols, my logical operators, right? What was the rule for the conjunction? At least one side had to be true in order for the whole thing to be true. So I got one side true, boom, I know this whole thing right here is true. So then he says, let's solve this side first because it's in the parentheses, and we'll just, bring down our, the E is what we started with, and then we substituted that for false, right? So to not confuse you, that's what he's doing here. So he's saying true or false. The whole thing's true because I have one side true. We still have our false here, right? So now we have to eliminate the horseshoe. What was the only time the horseshoe was false? The only time out of the 4 possibilities, and it turned out this was the one time. If you have a true antecedent and a false conclusion, let me go up. Whole thing was false. You just have to memorize the rule. And sometimes it might, take you a couple times of looking at these. So again, if I have a true antecedent, false conclusion, the whole thing's false. So what he's doing is, and we'll see a few examples of this on the homework, it turns out they're really easy. You just have to learn the rules. So you start with this. He gives you a substitution. He says, look, whenever you have an A or a D or an E, I'm going to give you, if they're false or true, plug them in, and then solve whatever's in the parentheses first, then solve, then. So he gives you the example. Then he says, here's some general strategy of solving these. Do the truth value of the larger components. That's what I was talking about in parentheses. Then do the smaller ones. And he gives you your little rules. Individual letters representing simple propositions. Okay, no problem. It's like B could be like something about a bus. Who knows what it is. Tilde is immediately preceding the individual letters. So if you're going to use a tilde, you got to make it go before. So anyways, he gives you a few rules. So he gives you another example here of these. He'll substitute in the true and falses based upon the rule above here, and then he'll solve. So let's just do this one. B and the C, they were both true. E turns out to be false. We have an A, that was true. Again, not to confuse you. He's just telling you very simply right here what to do. So we come down and we substitute, right? We've got all of our T's and F's, got all that. So it turns out we'll do this side first. We have a T and a T on a conjunction. Both sides have to be true for the whole thing to be true, so therefore it's true. What about this one? We have a false. Now it turns out this is a little cheat sheet for you. Anytime you have a conditional and you have the antecedent false, you literally don't even have to look at the other side. If this is false, the whole thing's true no matter what. How do I know that? Anytime I see a false inside the antecedent, which is the P, I know the whole thing's true. So I actually don't have to look at the consequent. I could just look at this. If I got a false, the whole thing's true immediately. As you do this enough times, you will see. You will start to memorize that little tiny shortcut. If you don't know what I'm saying, no problem. All that means to you is that you're going to look at this side. a true and a true, or if I have a true and then my consequence of true, the whole thing's true. You can look up at your chart. For some of you, if this side was a false, you know the whole thing's true immediately. But anyways, let's move down. Yeah, and you'll see here he's going to give you examples, and I will do a separate video and I'll work these out for you. All he's doing is he's taking this, he's substituting the C's, A's, and B's, or E's, F's, whatever, and he's giving you the truth values, and then he's saying solve them. So this one, let's do this one right here. We have a true or false. We have a conjunction, right? At least one side has to be true for the whole thing to be true, right? So we have this whole thing to be true. Then we negate it. Therefore, it's false. Why? Because we have a negation hanging on the outside. So we do this first, then we negate. We don't negate the T and we don't negate the F right away. We do not do that. Some of you are tempted in mathematics. You're like, oh, let me distribute this negation all the way through. So when I have a negation outside my parentheses, I'm going to go not T and not F, dude. And then I'm going to solve it. No. In logic, we do whatever's on the parentheses first. We solve for that, and then we just negate that afterwards, okay? And he does the same thing here. Not B, it's a not true. So we know, how do we get that? Because we know a B is a true. We take the opposite of true, which is a false. So we bring these all the way down. We have a false, horseshoe, false. We know that this combination is always true. So we know that this statement, this symbolic representation of reality, right, of multiple propositions, we know that this whole thing is true. And then we have a monster one here. You can do this on your own. What I'm setting you up and what Hurley's setting you up for is, what's the main operator? So this will be part of your homework. So when we look at one, we know we have to do what's inside the parentheses first, right? So we have a conjunction here, we have a dot, and then we have a horseshoe. We have to do those first, and then when we're done with those, at the very last thing we do is what? We do this guy, right? The one in the middle. So when Hurley says, what's the main operator? That's it. The main operator is the horseshoe. And what he means by that, that's the very last thing, or it's the main operator of the whole proposition, or of all these propositions. So it's the very last step you do. Let's do two. What's the main operator here? Just look at this first part. Is it this tilde? Well, we know when we come here, where do we start? We start with whatever's in the brackets first or whatever's in the parentheses first, right? So we only have parentheses. We do this first. Whatever's inside this, we negate it. Then the very last thing we do is this. So this turns out as the main operator, this horseshoe. It's the very last thing you do. Because you will negate this B. The B is a true, then you'll negate it, you're false. So you'll notice all the way down, it's the very last thing you do. What about this, 3? Even though we didn't do it, you don't have to do it to know what the main operator is. The first thing you see is brackets, right? So you know that you have to solve whatever's in the brackets first. Then you're thinking, oh my gosh. Then you got to solve 2 different parentheses. You got to solve this, then you got to solve that. Once you solve this side, you got to negate it. Then you've got to, whatever you get for these 2, which is down here, let's say we get that far, then you have to negate this. Wow. Done with the parentheses, and I get my T, right? Over here, I have to do whatever's in the parentheses first, right? I do all that mumbo jumbo, get my true, then I negate it. The very last step is this horseshoe the whole time. It's the very last thing you do. So it's called the main operator. How do I get there? Well, when you look at these compound components here, you say, look, if I got brackets or parentheses, I do those first, and then the very last thing will be this. I think this is just another method of him doing it, but he does it sideways. If you can follow along with that, good luck. Me, I like this method. I like taking what I have and working downwards and being very consistent. Each of my symbols line, or my operators line up. Each of my operators, all the way down. So I like working down. If some of you can see working left to right and you're more abstract that way, awesome. So I'm not going to go over this, but he's basically going to solve this thing the same way he would up here. And notice this is a different example, but he's going to solve it going this way. So there you go. Last little thingy. If we have a dot operator, it turns out the truth value of an M and a B, or a B and an M, it doesn't matter what order it's in, it's the same truth value. So she got married and had a baby, and she had a baby and got married. It actually, those two statements about reality, truth, as far as truth components, when you solve these, it's still the same. He fell off a ladder and broke his arm. Same thing as he broke his arm and fell off a ladder. If both are true, both are true. You can flip flop. You can have one of these in the same or different order. It turns out in English we like to tell you what happens first, but in logic it turns out the truth value is not affected by that. We're just taking two propositions about reality. What our main concern is the truth value of the conjunction, or this dot. That's what matters more than the order. So that's all he's saying here. Yes, this is more on the conditionals. You can read about this. And I think those are just more examples. So I think that wraps it up. You have 5 logical operators. You know how to solve them now, or you know how to get the truth value of each operator. They have different rules for each one. Learn those, and then in my next video, we will go into examples of your homework that you might have in MindTap or on the book. And that's pretty much it. So there you go. Thanks for listening and following along. Any questions, just let me know. And I will upload the second video not too long from now.